Hello, welcome to our ME Design final presentation for our whiteboard eraser gantry. I'm Dylan, and I'm joined by Andy, Ryan, Daniel, Ryan, and Will. So professors have a very limited time to fully cover their course material during their lectures. We've identified a problem in that manually erasing whiteboards is an inefficient and repeated process, and it takes valuable time away from the lecture. So the idea we came up with was a 2D eraser gantry with a cleaning fluid dispenser. This way, the lecture can continue while the board is being automatically erased by our gantry system. The automatic application of cleaning fluid will help prevent any smudges from dry erase markers, and because it's all one system, you no longer have to keep track of the eraser and cleaning fluid separately.
When thinking about the design specifications, we want to make sure that our device was faster than a professor just erasing the board. So we want it to be able to clean a 4-foot by 6-foot board in around 1 minute. The horizontal force exerted on the vertical rail should not exceed 45 newtons, and that's to protect the whiteboard from any damage. The cleaning fluid tank should also be easily accessible, so we place it on the front of the gantry, and cleaning fluid refills should be infrequent, which we decided was around 10 pounds of cleaning fluid. We also want it to be compatible with standard 4-inch by 6-inch erasers because we don't want the professor to be reliant on a company with a proprietary eraser to make the system operable. Now, it also must mount to the wall using steel bolts. It must have infinite life, and all parts should have a safety factor of at least 2 for all failure modes.
So this is an animation of our SolidWorks model. It's a basic gantry system where each axis is being controlled by a carriage that is being pulled by timing belts.
So the first part of our analysis were the components of our system, which were the horizontal beams and the vertical beam of the gantry. So for static analysis of the horizontal beam, the horizontal beams experience forces due to compression from the tension of the timing belts, as well as the weight of the system and the force of the eraser pushing out of the board. So we calculated that the maximum stress on the horizontal beam is 1970 psi, and assuming that a factor of safety of 2 is used, following ductile theory, we determined that the yield strength required is at least 3.94 KSI, which is satisfied by 440C steel.
When doing the fatigue analysis for this bar, we needed to find the minimum stress as well as the maximum stress. The minimum stress was found to be 46 PSI, which allowed us to calculate our mean sigma value and our amplitude sigma value. Using these values and a safety factor of 2, substituting into the Goodman equation, we found an ultimate strength of 6.56 KSI, which our 440C steel choice exceeds this value, so it is safe.
For the vertical beams, there are 2 main types of loading. There's going to be direct bending from the force of friction pushing along the board, and there's going to be the indirect bending in a perpendicular direction due to the moment from that friction. Based on linear bearing properties and like the hardness guidelines, we used 440 steel and used a 1/2-inch diameter, giving us a safety factor of 3.38, which is more than enough.
In order to find in order to determine if our beam failed due to fatigue, we had to find the stress at the maximum point and the minimum point. We define the maximum point to be in the center of the beam and the minimum to be as far away from the center as possible, or 2.4 inches away from the horizontal beam. We used the equations for maximum moment to find the maximum moment in the z direction and the minimum moment in the z direction. We then repeated this for the x-axis to find the maximum moment in the x and the minimum moment in the x. And then using the equations to find stress from moment, we were able to calculate the maximum stress in the z direction, the maximum stress in the x direction, and then the minimum stress in both directions as well. From here, we had to find the maximum and the minimum von Mises stress, which we used by plugging it into the equation to find those. And then after this, we had to find SE in order to do our fatigue analysis. And using this equation for SE, all we had to do is find the K factors. For KA, we assumed a KA value of 0.8 since we don't know our SUT yet. For KB, KC, KD, and KG, they're all equal to 1. And then for KE, it's equal to 0.814 due to 99% reliability. From here, we were able to find our SE in terms of SUT. Then we found our amplitude stress and our mean stress and used that with our SE or SUT and an assumed safety factor of 2 along with the Goodman equation to find our SUT of 63.17, which is significantly lower than our materials SUT of 110 KSI, which means that our vertical beam won't fail due to fatigue.
So for the buckling analysis of the vertical and the horizontal beams, the only force that's compressing the beams is the belt tension, as it was previously mentioned, and that is a force of 15 pounds. From that, we can calculate that the critical force on the horizontal beam would be 3,364 pounds, making the safety factor 224. And for the vertical beam, the critical force would be 394.3 pounds, making the safety factor 26.3. And so both vertical and horizontal beams are safe from buckling.
For our connections analysis, we needed to analyze the connections at the eraser mount and at the wall mounts. However, one of the wall mounts is different due to the presence of the fluid tank. For our connection analysis for our eraser mount, we picked 640 screws with 8 screws, 4 per carriage of SAE grade 1. And from here, we were able to find that the maximum shear stress was equal to 54.19 with a shear safety factor of 665. Since our shear stress comes from friction, the minimum shear stress would just be the negative of the maximum since it goes in the opposite direction. And using that, we were able to find a safety factor of 118.26.
The top corners of the gantry system were attached with a 2-bolt bracket. These screws were grade 5 UNC 1/2 inch, and they screwed into the wall. We made some assumptions that the system is at room temperature with 99% reliability and greater than 10 to the 7 cycles. We found the axial force and the shear stress on these systems to get factors of safety of greater than 1,000, which means they will not fail due to static shear and axial. And then for the fatigue analysis, we found the P mean and P amplitude, as well as tau mean and tau amplitude to get safety factors, the lowest of which being 27, which is still very safe.
For the bottom corner, we have to consider the cleaning fluid. So we chose grade 5 UNC 1/2 inch screws as well, but this time we are using 4 screws in a 2x2 square pattern. So for the shear analysis, we saw that the safety factor, not only for shear, but also for axial and loosening, were all greater than 1,000, meaning it's extremely safe. And for the fatigue analysis, we had to consider the tank as well as the weight of the bar. And that all turned out, the safety factor for all of that turned out to be 84.6, which is also extremely safe, meaning that we don't have any failure going on the bottom corner as well.
We have 2 powertrains in our system, one for horizontal movement and one for vertical movement. For the horizontal movement, we calculated that the eraser will require 10 full passes of the board, and we want to do this in 1 minute. We assumed a 2-inch pulley, and the torque needed to overcome the friction from the eraser was 2.2 pound-inches. With this 1 minute goal of ours, the speed that this pulley needed to spin is around 115 RPM, which requires a power of 0.04 horsepower. We found a motor with 0.08 horsepower and created a gear speed reduction of 54:1 to get this to the proper speed.
Yeah. So now that we're looking at the horizontal powertrain, we need to do gear failure analysis. So basically the maximum force that we found was on the last pinion and gear, and that was 5.33 pounds. And using that number, as well as some assumptions that we made on the right side of the slide, we got a maximum stress on the pinion of 2,025 PSI and a maximum stress on the gear of 1,620 PSI. Then we calculated the allowable stress based on the geometry of the gears, as well as the material that they are made out of. and got a maximum allowable stress for the pinion of 29,574 PSI and a maximum allowable stress on the gear of 26,482 PSI. Using those numbers, we found that the safety factor was 14.6 for the pinion and 16.3 for the gear, which means that overall our gearbox has a safety factor of 14.6.
For the vertical powertrain, not only does the motor have to overcome the force due to the friction, but also the weight of the carriage. So from this, we're going to need a torque of 9.4 pound-inches, and using a motor with a torque of 0.16 pound-inches, we're going to need an increase in torque of 57.5 times, while still maintaining the velocity of greater than 12 inches per second to meet our speed criteria. Using a 3-stage gearbox, we ended up with a 62.5 times increase in torque and a velocity greater than 12 inches per second at 14.4 inches per second.
For our gear failure analysis, we chose to analyze the maximum force, which was applied on our third segment, both on the pinion and the gear. For the applied stress, all the factors for both were the same other than the J factor. And for the allowable stress, they were made of different materials, meaning they had different STs. After calculating all this, we found that the safety factor on the pinion was 2.938 and the safety factor on the gear was 4.799, meaning that the overall safety factor on our vertical powertrain is equal to 2.938.
So we sourced all our parts from McMaster-Carr, and after totaling it up, our system cost $2,572. There's no commercial solution to this problem already, so we think that this is a fair price. But in the future, we could reduce this by buying in bulk and exploring different manufacturers.